Hello, students. Today I'll be talking about BJT transistor type. In this session, we'll look at the basic structure, operation, and characteristics of the bipolar transistor. As you can see, this is just an overview of the physical transistor type. Of course, we have different transistor type configured according to PN junction. Well, this transistor has been in this business world since 1960s. As you can see, the BJT or BJT transistor is simply consists of two PN junction, okay? And the forward base, as you can see, the PN junction is in a forward base, okay? So if we go to the right side, it is forward base. But then if we go back to the reverse, if we go this way, then NP will be our PN junction. In that way, it will be reverse base, okay? So there is a large depletion layer at the junction between N and P. So there is a depletion pair, so the holes can move or electrons can move in between. Let's skip this one. If we look NPN transistor current and voltages, this is the way we're going to assess for today. Okay, so I emitter, which is the current flow with that downwards to the emitter side. Okay, this I emitter is IB is plus current coming from that IC. Okay, and then VCE, which is VCE. So say for example, voltage between VCE here is equals to voltage CB, which is across this. This is the CB plus voltage across this area. Okay. So the PN junction between base and the emitter, which is base and the emitter, is in forward base. The voltage across it or VBE, we call it VBE, okay, is like a voltage of forward base, which is around between 0.6, 0.7 voltage for silicon, a diode. So the PN junction between collector and base, which is collector and base, is here or here, VCB or VCB here, simply, okay, is in reverse bias, VCB, which depends on the amount of collector current and external circuit, obviously. Okay, so opposite, inversely or opposite to NPN, this is a PNP. Okay, now the direction of the current is reverse-wise. So I emitter becomes I collector plus I base. Okay, like as you can see now, we can have a common base configuration. It could be NPN or PNP. Today we'll look at the NPN. Okay. If we look at NPN, also we can assess for a DC current gain, which is this current gain is this one is we can have this formulation, okay, where alpha is a common base DC current gain, which is sometimes close to 1 or 0.99 usually, and then this B or beta is a very large number. It could be from between 100 to 500. So if we use a comma emitter configuration, so for example, as you can see, common for PNP, or NPN or PNP in here, we have a common collector, common emitter configuration. Then what we can have is we have base current added with collector current. Okay, so in this scenario, we can have voltage across CE, which is across collector emitter. Okay, sometimes you can call it from all voltage from here to here, equal to VCB, which is VCB base VCB here. Okay, the voltage across here. Sorry, plus VBE, where VBE is somewhere here. Okay. So if we apply a base between collector and emitter, as long as VCE is greater than this, and it will the PN junction will be in a forward base. Okay, so we'll assess this one on Multisim software. So for the NPN transistor, I'm just focusing today on NPN. So IC, we can have alpha times I. Okay? Or IB from here, which is I emitter minus ICB, because I emitter is equals to I bias plus I collector. So from that, we can have I bias will be IE minus IC. Okay? And then if we replace IC using this alpha emitter or I emitter, then that will be 1 minus alpha times IE. Okay? From that IC, we will have alpha times IE, which is this, and we'll have beta is equals IC over IB. Okay? Where B is a common emitter, DC current gain, where we say that this is in range of 100 to 500 values. Okay? And the base is around just around 1. Okay? As we can see here, maybe to 1000. Okay? So what it means is we can control the collector current by applying a small amount of bias current. We'll see. Okay, I'm gonna skip this one. This is just equivalent circuit for now. And now we're gonna talk about mode of operation for NPN. Okay, for NPN, we will look at in the active region is VBE, which is voltage BE around to here. It is greater than 0.5. If it has to operate in active region, then this is true. Okay, what does this mean is then I collector will be BN times IB. Of course, we have active region cutoff saturation. So we need to follow this region. And now if we look at the characteristics of transistor, we normally have a forward base or base emitter. This that is B emitter or whatever. And then this is just collector, and this is bias BB or VBBB. Okay. So what we're saying is the transistor will conduct in forward base when IB will draw a lot of bias current. This is a base current when the voltage forward base is around 0.6, something around here. After here, when the voltage increases from 0 to 0.6, the collector current is still 0. But as it is above 0.6, then it slowly increases, as you can see. Maybe at 0.7, maybe somewhere here, maybe 10 microamp. 0.8, you can see 20, then it just go like this. And then, for example, maybe at 0.8882, maybe around 180 microamp, sorry. Okay, so this is in a forward base region. So VBE means the voltage across this, okay? Or voltage across VBE, okay? So this is in a common emitter, which is input characteristics, okay? The output characteristics is again, it is the plot is plotted against collector current versus collector voltage collector emitter. Okay, so the collector current is coming that way. IC is plotted against VCE plus this VCE. Okay, so which is this is an output. So what it means is how do we control the collector current is in a small amount of bias current, because what we're saying is IC is equals to beta times IB. Okay. So this is just the characteristics of input characteristics, sorry. And this is just still an output, but in our output characteristics, we have different scenarios. So in here, we have cutoff region. So that means the collector current is 0, although the voltage collector emitter is increased from 0 to 10. But in here, sorry, this is a cutoff. And then in here, all this region, the blue sharp, this is a saturation region where the transistor would not operate. But then in here, it is, active mode. So If you see, for example, bias current is 0 in here. In this region, bias current is 20 microamp, 40 microamp, 60, 80, 100. Okay. So this is this. And the mode of operation for active region is when the VBE or VBE across here, okay, is in a forward base when the voltage is above 0.6, which means this one, sorry, above 0.6. And voltage across CB, which is collector bias somewhere here, okay, will be in reverse bias when this is greater than 0, usually a large voltage, of course. So now if we look on here, this is our formula. So I collector is equal to beta times I bias, okay, which where I bias is equals to VBB minus VBE, the voltage across this drop, okay, divided by RB, by this resistance, okay. So then we have IB, and then from that, we have this relationship because IC, sorry, okay, now we have IC here, okay, this one, IC plus IB is equals to IE, okay. From that, we have the relationship, and then IC is equals to beta times IB, okay. So from that, so erase this one. Okay, erase it now, sorry. And then we have, this is an active region, for example, sorry, this is an active region formula. So if we look in here, when we have a small amount of IB, which is 22 microamp or 0.022 milliamp, and then this is an IB now, 0.022 milliamp, okay? And then we can have a collector current of 4.4 milliamp, okay? So which is with a small amount of bias current, we can draw or, have a large amount of collector current because we have, this is almost fixed value, okay? And then from that, we can have a voltage of 5.4 volt across voltage CE in here, in this region, okay? Because if we have 5 volt input, VBE in here, 5 volt, okay? And then if the transistor is in a conductor or in a forward bias, which is VB is 0.6 volt. So if this is VB is 0.6 volt, okay, then with a small amount of voltage, okay, we can have a small amount of current, okay? From that, we can have a large amount of current from here. So basically, we are controlling this by using this bias current, okay? And then we can have a large amount of voltage in the VC region or in the output. Okay, this is just the cutoff, region when we have bias, when we have no bias current. Basically, that means there is no forward bias of the transistor. Okay, because this is just a less than 0.5 volt, and saturation is when we have I collector current is less than beta times I bias. So when we have a small amount of collector current, that means we have large amount of bias current. That means it is a saturation region. Okay. The aim of this one is to have a small bias current and then let have large amount of collector current. Okay. So what we need to know? Well, a BJT can have common emitter input and output characteristics. And we need to understand mode of operation, which is active, cutoff, and saturation region. Of course, I'm not interested for today, this equivalent circuit or whatever signals. We also need to know common base and emitter DC current gain, but I'm not concerned today. So I'll focus today mainly in this region, okay? Or in here as well. So I've done this one using calculation Excel spreadsheet. Okay, so as we discussed already, this is the input characteristics of the NPN. So as you can see, the forward bias is when the VBE reaches 0.6 volt, then the bias current increases significantly. Okay, which means the transistor is working or drawing a lot of a base current when the voltage is above 0.6. So when we do the testing, we can have this configuration, VCE 1 volt, 10 volt, or 20 volt. But then, as you can see, when we have in here input, okay, when we have input voltage here, okay, when we increase from 0 to whatever, increase in here, then the plus minus in here, okay, V is VBE, and then plus minus in here is VCE, okay, and then this is VBE, okay, because this is emitter, okay. Then, as you can see now, until 0.6, the VBE, until 0.6, the bias current is almost up to 0, I can say 0.3, maybe microamp, very small amount. But as soon as we reach 0.6 volt, then this starts to close to 1 microamp. Then when we increase above 0.6, then this goes high. That means the transistor is operating in a forward region, which means it increases the bias current. Okay, so that implies that satisfies this kind of configuration. Yeah, okay. And similarly, whether we increase this whether we put 5 volt, 1 volt, 20 volt, they are all the same. As you can see, for example, at 0.6, this is 0.3, 0.3, 0.336, they are the same. So for example, when this voltage V input is 10 or 11.5, then it is such, it just, this voltage on the forward base, it remains within 0.6 and 0.7, as you can see, just around this area. So that's why you can see still no increase of region of the voltage. So then, but the bias current is increased from 1 microamp up to maybe 1000 microamp or 1 milliamp. Okay. So, well, how do I get this value? Well, I just built in here a simple transistor. Okay. And as you can see, I just vary this voltage from 0 to maybe whatever, 100 volt. And then you can measure VBE here using voltmeter. Okay, sorry, in here, voltmeter. And then you can also measure current in series, which is IB. This is IB, okay? IB, and this is just the voltage. And then in here, again, the current in series, which is IC. This is IC, and then this is just voltage VCE, okay? So this is the technique how I measure this value. Whether we increase this 1 volt in here or 10 volt, 20 volt, it doesn't matter. What matter is when we increase this voltage from 0 up to whatever, infinity large number, then this voltage moves from, it conducts, it provides IB, this current when it is above 0.6 volt, okay? Up to maybe 0.77, as you can see here, sorry. As you can see, the maximum 0.77, then in here above 100 volt, then it just draw around 1 volt, but depend on the device. Okay, so now as you can see, you can see the actual value. For example, when it's 1 volt, then this plus minus in here, the VBE, yeah, gives 638 millivolt or 0.63 volt. 0.63 volt, okay? Then it gives the current bias current of, I bias current in here, it gives around 3.62 microamp, okay? Now, what does this mean is then the current in here, the collector current is 964 microamp. you imagine with a small amount of bias current, which is 3.6 microamp, we draw 900, close to 1000 microamp. Okay, that's why we draw a collector current by beta times IB. With a small amount of bias current, we can have a large number of collector current. Okay, and then of course, this is just the forward region. I plot the results, and just around 0.6, it increases a lot of bias current. And then in here again, it's the same, whether we increase the voltage in here, it doesn't change the characteristics. Okay. And then I plot this value on Multisim Software. So we just increase the voltage input. We just access this one and this transistor type, and then it gives us similar to the theory forward base. Okay. And then again, this is the output characteristics. So okay, ignore this one for now. But if you look in here, it is just in here is saturation region, and then this is cutoff frequency. Cutoff region, and this is just an active region. Okay, now I'm gonna take you to okay, this is the simulation. I'm gonna show you. I'm just gonna show you on Multisim. So say for example, this is a transistor. You can just build it from the component. It's just very easy. You can just find it from here, from transistors here, that kind of type, okay? And we just need to go to simulate analysis. And I'm gonna give 1 volt in here, 1 volt, okay? And then I'm gonna assess the input characteristics. So what does this mean is in here we have a testing procedure. So we can just VBB means the input voltage as you can put it, and then I can plot against. I think I need to put VCE, then I need to put output IB. Sorry, is it my yeah, this is now my input characteristics. If you look in here, it's just around 0.6. It's just going high into the forward region basically. So so this is at 1 volt. I can change this one to different voltage. So this is the bias current. This is the voltage in VCE. Okay. So if I put 10 volt again on this one, it's still the same. Okay. And if I put 100 volt, it's still the same input. So the bias current is stable or increasing when the voltage forward is above 0.6. Actually above 0.68. Okay. And then to see the output characteristics, we can assess using a small bias current to have a large amount of collector current. Okay, so let me just configure this. Now we gonna put VCE in here, which is output voltage against bias current. So I'm gonna control the output current using bias current. So if we look in here, using a small amount of bias current, I can have more collector current. So in each, this is the output, which we discuss on the theory. And if you look in here, if you look in here, this is just what it means. Okay. So this characteristic. So we on this collector current, we have this collector current, but a different bias current. So if I increase, for example, this one, I can just increase to 1,100, sorry, microamp. If I do this again, run, we can control, we can change the different values to see the output for bias current. With a smaller bias current, for example, in here, we can have more collector current. Of course, this is individual. We can click it in here. We can just yes, it's just for the cursor to show, but this is the input, output in here. So basically what it means is we can just move this cursor to read a different reading. And then again, you can just play with in here. Just to see a different output. You look in here. So we can just click in sweep. Yeah, if you look in here, we can just play with a different region. So you will have an option to tick which one individual to assess individually of the bias current against the collector current or the voltage in output. So basically what it means is with a small amount of bias current, for example, we can have a large number of collector current. Okay. All right, that was it for today. And the next time we'll go through the different characteristics of this to assess the small signal scenario. Okay, thank you for watching this.